A soda can crush as flat under one finger, yet it can survive being shot into orbit. A sheet of foil tears if you look at it wrong. Yet the same metal holds up the wings of a jet at 500 miles per hour. It's lighter than almost any other metal on Earth. Yet it never rusts, never corrodes, and lasts for decades outdoors. That shouldn't be possible from something this soft, this cheap, and this common. So how does a dull red rock, dug out of the ground by the billions of tons, become one of the strongest, lightest, most trusted materials on the planet, turned into everything from kitchen foil to spacecraft? Let's step inside and find out. Aluminum is the most abundant metal in the Earth's crust, more common than iron. And yet, for most of human history, nobody could get it out of the rock. In the 1800s, aluminum was worth more than gold. Napoleon III reportedly gave his most honored dinner guests aluminum silverware, while everyone else made do with gold. Even the tip of the Washington Monument was capped with aluminum in 1884. Not out of style, but because at the time it was one of the most expensive metals a builder could show off. A shining 9-pound ornament that cost as much per ounce as silver. Everything changed within just a few years, once two young chemists working independently on opposite sides of the Atlantic, Charles Martin Hall in the United States and Paul Héroult in France, discovered at almost exactly the same time, and without knowing about each other's work, the electrolysis method that would collapse the price of aluminum by over 90% within a decade. It took over a century of chemistry to turn this precious metal into something so cheap it's thrown away after one use. It starts nowhere near a factory. It starts in open pits in places like Australia, Guinea, and Jamaica, where excavators tear into reddish-brown rock called bauxite. Bauxite isn't pure aluminum. It's a mix of aluminum oxide, iron oxide, and clay, which is why it has that rusty color. Massive dump trucks haul the raw ore to a nearby processing plant because bauxite is too heavy and low value to ship far in its raw form. From here, roughly 4 tons of bauxite will eventually become just 2 tons of alumina, and from that, only 1 ton of finished aluminum metal. Everything that follows is really a story of subtraction, stripping away impurities, piece by piece, until almost nothing but pure metal remains. Mining companies don't just dig and leave either. Because bauxite deposits sit close to the surface, mining crews typically strip away only a shallow layer of topsoil to reach it. And once an area is exhausted, that same topsoil, along with the native seeds and plant materials saved from the original clearing, is spread back over the land so forests can be regrown on top of former mine sites. It's one of the few heavy industries where the landscape is expected to look almost the same 20 years later as it did before the first excavator arrived. The crushed bauxite is mixed with hot sodium hydroxide, essentially a powerful lye solution, inside massive pressurized tanks called digesters, heated to around 270 degrees Fahrenheit. This dissolves the aluminum oxide out of the rock while leaving the iron oxide and other impurities behind as a thick sludge known as red mud. The remaining liquid, now rich in dissolved aluminum, is filtered and cooled until white crystals of pure alumina, aluminum oxide, precipitate out, almost like sugar crystallizing from syrup. The leftover red mud is not simply discarded. Because it's mildly caustic, it has to be carefully stored in lined containment ponds, and engineers are constantly researching new ways to repurpose it in things like cement and road construction. This is where things get extreme. The alumina still isn't metal. It's an oxide bound tightly to oxygen atoms at the molecular level, and that bond is stubborn. To break it, the alumina is dissolved into a molten bath of cryolite inside massive carbon-lined steel tanks called reduction cells, or pots. Each pot is then blasted with electricity, hundreds of thousands of amps, running between carbon electrodes submerged in the molten mixture at temperatures near 1,750 degrees Fahrenheit. This electric current rips the oxygen away from the aluminum atoms at the molecular level. Liquid aluminum, now pure, sinks to the bottom of the pot, while the freed oxygen bubbles off and combines with the carbon anode to form carbon dioxide. A single smelter can house hundreds of these pots side by side, running continuously day and night for years without stopping. because restarting a cooled pot from scratch is so costly that plants treat a shutdown almost like a medical emergency. If a pot ever goes cold, the molten bath inside solidifies into a solid block, and getting it running again can take weeks of careful reheating rather than the flip of a switch, which is why smelters build in backup power systems specifically to keep the pots alive through outages that would barely inconvenience an ordinary factory. Every day or two, workers use a vacuum siphon called a crucible to tap off the molten aluminum pooled at the bottom of each pot, glowing white hot at over 1,200 degrees Fahrenheit. This liquid metal is transported to a casting facility where other elements like magnesium, silicon, or copper are often blended in while it's still molten. This is where pure aluminum becomes an alloy, a custom recipe engineered for a specific job. The alloy used in a soda can needs to flex without cracking. The alloy used in an airplane wing needs to resist fatigue after millions of takeoffs and landings. The alloy used in a bicycle frame needs a completely different balance of strength and weight. The molten mixture is then poured into molds to form massive rectangular blocks called ingots, each one weighing thousands of pounds, and cooled under tightly controlled conditions so the metal solidifies without internal cracks. Before that molten alloy is even allowed to touch the mold, it's tested. Technicians pull small samples and run them through a spectrometer, which reads the exact chemical composition down to a fraction of a percent. Because being off by even a small amount of magnesium or silicon can change how the finished metal bends, welds, or fails under stress decades later. A batch that doesn't match its target recipe gets sent back to be adjusted, rather than being allowed to move forward and become an unpredictable window frame or a fatigued airplane rivet years down the line. From here, the ingots are reheated and fed through enormous rolling mills, pairs of steel cylinders that squeeze the metal thinner and thinner with each pass, sometimes exerting thousands of tons of pressure. A single ingot, originally a few feet thick, can be rolled down into a coil of sheet metal thinner than a human hair, destined to become foil, or kept thicker to become the body panel of a car or the skin of an airplane. Other ingots skip rolling entirely and instead go through extrusion, where the heated metal is forced through a shaped steel die under enormous hydraulic pressure, coming out the other side already formed into a window frame, a ladder rail, or a heatsink. The same way toothpaste takes the shape of its tube. Raw aluminum straight off a rolling mill or extrusion press is soft, dull, and completely unprotected. Many products go through a finishing process called anodizing, where the metal is submerged in an acid electrolyte bath and once again hit with an electric current. This time, instead of pulling atoms apart, the current builds up a thin, extremely hard layer of aluminum oxide directly on the surface, essentially growing the metal's own natural rust into a protective armor on purpose, under controlled conditions, rather than letting it happen randomly outdoors. That anodized layer is also porous enough to absorb dye, which is how aluminum water bottles and phone cases end up in bright, saturated colors that never chip off like paint would. Here's the detail most people never think about. Making 1 pound of new aluminum from bauxite consumes as much electricity as running a household refrigerator for an entire month. Aluminum smelters are so power-hungry that they're often built next to hydroelectric dams specifically to feed them. Some smelters use more electricity than a small country. But here's the flip side of that. Recycling aluminum uses about 95% less energy than making it from scratch, because you skip the entire electrolysis step. That's why the aluminum can in your recycling bin can be melted down, reformed, and back on a store shelf as a brand new can in as little as 60 days. It's also why aluminum is considered one of the most quietly recycled materials on Earth. Nearly 75% of all the aluminum ever produced since the metal entered mass production is still in circulation today, just reshaped over and over again. Unlike some materials, aluminum doesn't degrade in quality no matter how many times it's melted down and reformed, which means the soda can in a recycling bin today could, in theory, have started life as a fighter jet part, a kitchen pot, or a window frame decades earlier, quietly passed through dozens of shapes without ever wearing out at the atomic level. From a scoop of rust-colored rock, through scalding chemical baths, Through a jolt of electricity strong enough to power a small town, aluminum emerges, light enough to help lift an aircraft off the ground, strong enough to protect a soldier's helmet, and durable enough to outlast the building it's used in. It leaves the mill as coils of sheet metal, extruded rods, or cast ingots, headed for factories that will turn it into cans, foil, window frames, and airplane fuselages. A metal once more valuable than gold, now so common most of us throw it away without a second thought. That's how a rust-colored rock, dug from open pits on the other side of the world, becomes the can in your hand, the foil in your kitchen drawer, and the wing of the plane overhead. Precision, chemistry, and raw electrical power most of us never think about, until now.